So last day we were just finishing up the idea that lengths contract. Objects that are moving get shorter in the direction that they're traveling. And we had said if you actually go the speed of light, photons don't experience distance at all. When they leave a distant star, as far as they're concerned, they didn't even travel the distance in between that star and us. They were simply here. I did promise you the possibility of traveling backwards in time. So again, not on your test, but for nerd credit, put your pencil down, look up.
Einstein's general theory of relativity describes gravity in terms of warps and curves in space and time. And it's the time part that shows us that a certain kind of time travel is allowed by the equations of the general theory of relativity. Let me describe how that goes. So imagine that we have a region of space and we've got a spaceship. And to keep track of time, we're going to put a clock on the ship and a corresponding one back on Earth. And now we're going to go on a journey. We're going to take the ship and go to the edge of a black hole. Careful not to fall over the edge, so we just hang out near the edge of the black hole. And Einstein tells us that time elapses more slowly in the presence of a strong gravity field, a strong gravitational potential, which means when the ship comes back, there's a time difference between the two clocks. In this case, a 30-year time difference.
So the purple ship has traveled 30 years into Earth's future, which we've already said, Fahim, is totally doable. This time, the time dilation wasn't because it was traveling really, really fast near the speed of light. This was because of gravity near a black hole. That's general relativity. We'll talk about that tomorrow. Okay.
Between them. So if a person gets out of the ship and revisits with his or her friends on Earth, that person will find that their friends are 30 years older relative to the amount that he or she has aged. For this person, it's 2050. Everyone on Earth says it's 2080. That is time travel to the future, courtesy of general relativity, and in this case, time spent near the edge of a black hole. This is not at all controversial. Everyone who understands general relativity agrees that, at least in principle, this is how things work. The deep question, though, is, what about getting back? Can you travel back in time? And the thing is, we do not know the answer to that question. Most of us think it's not possible. But it's interesting that there are some proposals that have been put forward for how you just might be able to travel back in time. And let me describe one of them to you. It involves the idea of what's known as a wormhole. You may have encountered that in other settings. A wormhole is just a tunnel through space that acts like a shortcut. So if you want to go from this location to this location, you can go the long route on the outside, or you can go the short route through the wormhole itself. Now let's rerun that little scenario of a rocket going to the edge of a black hole, but now in the presence of a wormhole. So we bring in a rocket ship. Imagine it can tow the mouth of a wormhole toward the edge of a black hole. And if we do that, we'll find, just as we did a moment ago, that time elapses more slowly near the edge of a black hole than far away. So if this ship then returns to the vicinity of Earth, by the time it gets back to its starting point, there'll be a time difference between the two clocks. Again, in this case, a 30-year time difference, just as we found before. Now notice, for the moment, the wormhole hasn't really played any role. It just went along for the ride. What we're now going to do is analyze exactly the same situation, but take the perspective of looking through the wormhole itself to see how time hooks up through the wormhole from one opening to the other. So let's do exactly the same experiment. Take that wormhole opening, tow it to the edge of a black hole. But now what we're going to do, as I mentioned, is look through the wormhole itself. And the math shows that the two clocks at each opening of the wormhole, when viewed through the wormhole itself, agree with one another. There is no time difference between them. And that's quite interesting because it means that when this rocket ship goes back to the vicinity of the Earth, If we now consider the two clocks, the one at this wormhole opening and the clock at that wormhole opening, those two clocks will agree with one another. So what we've done is we've looked at one and the same situation from two different perspectives. The first perspective was looking at how time hooks up outside of the wormhole, where we found a 30-year time difference. And the second perspective looked at how time hooks up through the wormhole, where we found no time difference at all. Now, it's not that one of these is right and the other is wrong. They're both correct, just analyzing the same situation from two different viewpoints. And that's where the power comes from. Because imagine we started Earth at May 2080, and we go on a journey from one wormhole opening to the other, and now we want to go through the wormhole itself, which means we need to invoke this picture, the relevant one for time going through the wormhole. So we start here, we go into this picture, and we go through the wormhole itself, and we'll end up near Earth at May 2050.
So you started at 2080, and at least in theory, you could end up back at the Earth in 2050, 30 years in the past. This does not violate any of our currently understood rules of science.
We started at May 2080 near Earth. We wound up at May 2050 near Earth. We've gone 30 years into the past. Time travel into the past. Now, the reason I say this is speculative is that we don't know if wormholes are real. They do solve the equations of general relativity, but that doesn't mean they're actually out there in the universe. And even if they are real, nobody knows if you could pass through a wormhole. They seem to be unstable objects. The math seems to suggest you need some sort of exotic material to pry the throat of a wormhole opening so that it won't collapse in on itself. So with those two caveats in place, we don't know if wormholes are real, we don't know if they're stable, we at least come to this surprising conclusion that it's at least possible that time travel to the past might be something within the laws of physics. I should say most of us think that when we understand physics better, we're going to find some way to rule this out. But as of today, it's still at least a tiny possibility that time travel to the past might actually be something that could be accomplished.
So, if we ever develop the technology to tow a wormhole around, maybe. Next page over. It gets even stranger, but cooler. Gonna make it, Acacia? You awake? Okay. Acacia, not only does a moving object experience time slower than an object at rest, not only will a moving object shrink compared to an object at rest in the direction of travel, Einstein showed us that as objects speed up, their mass increases. And this is governed by this equation here. Can you find it on your green formula sheet so you know where it is? Oh, it can also be written using the Lorentz factor as m equals m0 over, and then we use that gamma as the abbrev for square root. What we just need to do is talk about what's m0 and what's m. Unfortunately, m0 is not the mass on board the spaceship. m0 is the original mass at rest, or speed zero. So there's two ways for you to remember what m0 is. It's the original rest mass, the original mass at rest, or it's the mass at speed zero at rest. And m is what we call the relativistic mass. And your hint is it will always be larger than m0. As objects speed up, their mass increases. Question, Aiden? You're good? Good? Okay. Let's look at this then. Suppose an object had a mass of 10 kilograms at rest. That 10, is that m or m0? at rest. This is m0. This is the original mass at rest. What would its mass be if it was traveling at that? Let's see if we can go straight to plugging in numbers. So this is asking us to find the relativistic mass. So I guess it's going to be m equals 10 divided by the square root of 1 minus. For A, is there going to be a do you see, do you see, do you see? What the 2.5 times 10 to the 8th all over 3 times 10 to the 8th square. Wait. Look up before you start typing. There isn't a do you see, do you see, do you see, but is there a times 10 to the 8th on the top? Is there a times 10 to the 8th on the bottom? Those will cancel. It's probably easier just to type 2.5 divided by 3 on my calculator. So here we go. It's going to be fraction button if you got it, 10 if you don't, divided by square root, open up a bracket, 1 minus another bracket, 2.5 divided by 3, close off the mini bracket, squared, close off the square root. Try typing that one in, because there is going to be one like that on your test, and you want to make sure you know how to type these in successfully. You are going to get an answer bigger than 10. If you don't, you've made a mistake. And I get 18.1 kilograms. See if you get the same thing. Same thing? Okay. Anybody else? I need confirmation because I might have made a typo. Yep. 18.1. Why did I write 11? 18.1 kilograms. Series 8. Okay. Zaina, in B, did they give me the speed in meters per second or as a percentage of the speed of light? So I can do the do you see, which is kind of nice. So it's going to be m equals the original mass at rest was still 10, square root of 1 minus 0.99 c over c all squared. Do you see? Do you see? Do you see? That's what I said, 0.98. I was looking at c for some reason. Thank you. So if I get up my calculator and I go 10 divided by square root bracket 1 minus 0.98, so at 98% of the speed of light, this 10 kilogram mass will have a mass of 50.3 kilograms. Scott, how fast are we going in part C? You know what, Scott? Let's be lazy. I think I can just backspace and change the 8 to a what? Change the 8 to a, yeah. 99% of the speed of light. Now 70.9 kilograms. The fastest we can get stuff going is at the Large Hadron Collider. It gets protons up to 0.999999991. 1, 2, 3, 4, 5, 6, 8 nines and then a 1. So where you have the 99, try putting 8 nines and then a 1. Oh. And then don't forget the squared. If we could get a 10 kilogram mass up to that speed, what will its mass be at that speed? Mal, what'd you get? That's my way of saying, I don't think you're typing this one yet. So, for part D, 8 nines and a 1 squared. Chloe, did you get holy 74,500 and, yeah, 40? This is why you can't get any object with mass up to the speed of light, because the closer you get, the heavier it gets. In fact, if you try putting in C, you'll get an infinite answer. Do you know how much energy it takes to get an infinite mass to the speed of light? An infinite amount of energy, more energy than there is in the universe. So any objects with matter can get really close to this. By the way, the amount of energy the Large Hadron Collider uses to get protons, which are pretty light, to that speed is enough to power a small town. So it's taking a tremendous amount of energy. Okay? So one of the reasons that light is the cosmic speed limit is that. What's your homework? You can try every question here. The answers are at the very, very end, and I will put out a showing all my steps online answer key as well. But let me hit pause here. First, put your pencils down.